Discrimination by regression. In regression, the probabilistic model is r to the t equals to y to the t plus epsilon, where epsilon is approximated by the normal distribution of parameter 0 and sigma squared. If r to the t is in either 0 or 1, y to the t can be constrained to lie in this range using the sigmoid function. Assuming a linear model, in the two classes we have that r to the t equals to sigmoid of w transpose times x to the t plus w0, which is equals to 1 divided by 1 plus the exponential functions of minus of w transpose times x to the t plus w0, and then the sample likelihood in regression, assuming that r conditioning on x is approximated by the normal distributions of y and sigma square, is that L, the likelihood functions of w0 conditioning on x equals to the multiplying for all t of the following term. 1 divided by the square root of 2 pi times sigma, then times the exponential of the following minus r to the t minus y to the t to the square divided by 2 times sigma square. And if we maximizing the log likelihood is minimizing the sum of square errors, that is the expectations of w0 conditioning on x is equals to 1/2 times the sigma summing for all t of the square of r to the t minus y to the t, and using gradient descent we get delta w equals to eta times the sigma t summing for all the term of r to the t minus y to the t times y to the t times 1 minus y to the t times r to the t, and delta w0 equals to eta times sigma t of r to the t minus y to the t times y to the t times 1 minus y to the t. And this method can also be used where there are k greater than 2 classes. The probabilistic model is r to the t equals to y to the t plus epsilon, where epsilon is approximated by the normal distribution in k of parameter 0 and also sigma square times ik, where ik is the identity matrix. And assuming a linear model for each classes, we have that yi to the t equals to the sigmoid of wi to the transpose times x to the t plus wi0, which is equals to 1 divided by 1 plus exponentials of the minus of the function wi to the transpose times x to the t plus wi0, and then the sample likelihood is L of the set wi0 of conditioning of index I conditioning on x equals to the multiplying for all t of 1 divided by 2 pi 2d k over 2 squared times the absolute values of sigma to the 1/2 times the exponential function of the following: the minus of the norm of r to the t minus y to the t to the square divided by 2 times sigma squared. And the error function is the error of the set wi0 with index I conditioning on x equals to 1/2 times sigma t summing for all the square of norm of r to the t minus y to the t, which is equals to 1/2 times doubling summation summing for all t and summing for all I of the term, the square of ri to the t minus yi to the t. And the updated equations for I equals to 1 to 3 until k are delta wi equals to eta times the sigma t of ri to the t minus y to the t times y to the t times 1 minus y to the t times x to the t, and wi0 equals to eta times the sigma t of the term ri to the t minus y to the t times y to the t times 1 minus y to the t. But note that in doing so, we do not make use of the information that only one of yi needs to be 1 and all others are 0, or that the sigma t summing for all y t is equals to 1. And the softmax function of equation 10.29 allows us to incorporate this extra information we have due to the outputs estimating class posterior probabilities. Using sigmoid outputs in k greater than 2 case, we treat yi as if they are independent functions. Note also that for a given class, if we use the regression approach, there will be updates until the right output is 1 and all others are 0. This is not, in fact, necessary. Because during testing, we are just doing to choose the maxima anyway. It is enough to train only until the right output is larger than others, which is exactly what the softmax function does. So this approach with multiple sigmoid outputs is more appropriate when the classes are not mutually exclusive and exhaustive. That is, for an x to the t, all ri to the t may be 0, namely x to the t does not belong to any of the classes, or more than one ri to the t may be 1 when classes overlap. Notes: the linear discriminant, due to its simplicity, is the classifier most used in pattern recognition. And we discussed the case of Gaussian distribution with a common covariance matrix in Chapter 4 and Fisher's linear discriminant in Chapter 6. And in this chapter, we discussed the logistic discriminant. In Chapter 11, we discussed the perceptron, that is, the neural network implementation of the linear discriminant. In Chapter 13, we will discuss support vector machines, another type of linear discriminant. Logistic discrimination is covered in more detail in Anderson, 1982, and in McLaughlin, 1992. Logistic sigmoid is the inverse of logit, which is the canonical link in case of Bernoulli samples. Softmax is its generalization to multinomial samples. More information on such generalized linear models is given in a McCullough and Neilder in 1989. Generalizing linear models by using nonlinear basis functions is a very old idea, and we will discuss multi-layer perceptrons, Chapter 11, and radio basis functions, Chapter 12, where the parameters of the basis functions can also be learned from data while learning the discriminant. Support vector machines, Chapter 13, use kernel functions built from such basis functions.